Hello, this is Math 2270 coming to you from the College of DuPage and for summer 2020, and the title of this lecture is Higher Order Linear Differential Equations and Such Preliminary Considerations. In Chapter 2 and also in Chapter 3 we were solving a few first order differential equations because they were spatial types like separable, linear, exact, homogeneous, and Bernoulli, Riccati's, and Clairaut's, and so on and so forth. Even though the solutions of these equations were in the form of a one-parameter family, this family, with one exception, did not represent the general solution of the differential equation. Only in the case of linear first-order differential equations were we able to obtain general solutions by paying attention to certain continuity conditions imposed on the coefficients. Recall that the general solution is a family of solutions defined on some interval I that contains all solutions of the DE that are defined on I. Because our primary goal in this chapter is to find general solutions of linear higher order differential equations, beginning with second order, we do examine some of the theory of linear equations. Some of this stuff will be familiar to those of you who studied linear algebra. Those of you who didn't, you will be okay. We will teach you all the linear algebra you need to know. Okay, so let's start with fundamental thing, and that is that this is an initial value problem. But this is this is not a first order initial value problem that we talked about with Picard's theorem. This is an nth order differential equation because it's derivative of the nth order, and instead of having one initial condition, we have n initial conditions. And the reason this is an initial value problem is because x0 is x0 always here. And there is a theorem that is like Picard's theorem that says if those coefficients and the right-hand side are continuous, and if none of them equal to 0, and this is kind of a big deal. I said we kind of are not worrying about that in the early going of this course. That becomes a singular differential equation problem and actually is much more formidable that we will study later in this course. But for now, I'll just say they're not equal to 0. So if x0 is any point on that interval, then there is a solution of the initial value problem called 1 exists, and it is unique. So it's kind of like Picard's theorem again. So this is a worthy problem to solve, and we will be focusing much effort on solving problems that are like this. Now, a boundary value problem is different because we have, in some sense, this is a second order boundary value problem. But you see, this is different because this point is not the same as that point. You can think about those as being different ends of a pipe or something like that. So you see, these aren't the same, and that makes it into what is called a boundary value problem, or BVP. Now, these are way important, way different, and not today are we going to talk about those. But the situation is different because you can have multiple solutions, you can have no solutions. The existence theorems are much different there, and the solution techniques are much different there too. It's a little bit surprising what a difference those initial conditions make, but they really do. In fact, I shouldn't say initial conditions, these conditions, either boundary conditions or initial conditions, makes a big difference. Okay, now, so this is what a nth order linear differential equation looks like, but if I set it equal to 0, I say it's homogeneous. Okay, and realize that that is not the same homogeneous as we talked about before. It just means this side is equal to 0. If the right-hand side is not equal to 0, we call it non-homogeneous. And just to save time, we're not always going to repeat that all these things are continuous and they're not equal to 0. Just say, yeah, I'm doing that as kind of a global assumption as we're going forward. Okay, now we're going to be talking about differential operators, and you might remember from your Calc 1 class, they talked about this notation and then never really used it. Well, this is where we're going to use it kind of big time. So the nth derivative means I use a capital D here, and I take these derivatives. So you see what happens is, if I were to look at this, that tells me that this is going to be 5x cubed times y triple prime minus 6x squared times y double prime plus 4x times y prime plus 9. If that's operating on y, that's the differential equation that I would get for that. And so in general, a differential operator that has a bunch of those things in it is called L. So you see we can apply L as an operator, and that means we're taking the derivatives. And in fact, there's some other examples up here that you can look at as well. Now this is a linear operator because when you take the derivative of a constant times the function is a constant times the derivative of the function, the derivative of the sum is the sum of the derivatives, and we call this a linear operator. You guys all know that, and that is what makes many of the theorems that we're talking about work, because these are linear differential equations, so the differential operators will behave in that way. Now, this theorem says if you add a bunch of solutions to a homogeneous differential equation, they have to be a solution to a homogeneous differential equation, they're still a solution, and that's because it's linear. And that means that a homogeneous linear differential equation will always possess the trivial solution of y equals 0. That just means all the c's are equal to 0. Now, we are concerned about getting a set of linearly independent functions, and here we define that. This is the same linear independence that you talk about in your linear algebra course. So a set of functions is linear dependent if you can find constants c1 through cn, not all 0, such that they add together is equal to 0. That means that one of them is a linear combination of the other, or perhaps even more like that. But if they're independent, if that's not true, if they're not dependent, then they're said to be linear independent, and linear independence is a good thing. Now, you might say, wow, that's really complicated, and people in the linear algebra class spend much time doing it with that definition. In differential equations, we have something that's a little bit better. There's a guy named Joseph Wronski, and he is famous for this. So this is the definition of the Wronskian. So suppose each of these functions, f1 through fn, possesses at least n-1 derivatives, then the determinant. And you do need to review how to calculate determinants going through this, so I'm giving that to you as a little bit of a side assignment here. Okay, so the Wronskian of this is equal to, you put the functions across here, you put the first derivatives across here, you do that all the way, and you go down to the n-1 derivatives. That means this is an n minus 1 by, let's see, it's actually an n because these are derivatives. So this is an n by n matrix, and we're taking the determinant of that. So the determinant, the Wronskian of this, is the determinant of that. You should look up the determinants again to remind yourself how to compute those. Is called the Wronskian of the functions, and here's the big theorem. Let y1 through yn be n solutions of the homogeneous linear nth order differential equation on an interval I, then the set of solutions is linearly independent on I if and only if the Wronskian does not equal to 0 for every I in the interval. Kind of a big deal. What we're really seeking is a fundamental set of solutions, because if you have a fundamental set of solutions, every solution will be a linear combination. I guess that's what this theorem says. So if you have a fundamental set of solutions, that means you have n of them, it's an nth order differential equation, and they're linearly independent, then the general solution of the homogeneous linear nth order differential equation will be some sum of those. That was a lot of definitions and things like that. We're going to apply this in 14.1. See you there.